control work, Nurbakyt, Shyryn questions basic concepts of classical mechanics. Classical mechanics studies the motion of objects, and we can actually distinguish three kinds of motion: translation, rotational, and vibrational. Translational motion is, for example, a block sliding on an inclined surface whereas the wheels on a yard are in rotational motion. And vibrational motion. Vibrational motion can be realized by two masses that are connected by a spring, or considering a tiny molecule where two atoms are connected via the molecular bond. And second questions. Right body rotating about the fixed axis. What is kinematic of rigid bodies? In kinematics of particles, we have studied about direct linear motion, curved linear motion, projectile motion, relative motion, and dependent motion. We had assumed that the whole mass of the body is concentrated at a single point, that is center of gravity. And in kinematic of rigid bodies, we will learn about motion analysis of rigid bodies without involving the forces responsible for the motion. Study of kinematics of rigid bodies is important for the design of gears, cams, and mechanisms used for many mechanical operations. And the translational motion. In a roller coaster, the scattering arrangements in the car is such that every portion is parallel to one another. When the car is moving on the track, the pace traced by every portion is parallel to one another, so a body is said to have a translatory motion if an imaginary straight line drawn on the body remains parallel to the original position during its motion. And the translation motion is further divided in linear translation motion and curvilinear translation motion. And the arrangement of the piston and the crankshaft is as shown. Then the craft rotates. The motion of the arrangement begins. Piston will move in the given slot, performing a rectilinear translation motion, and the motion of the crankshaft will perform a curvilinear translation motion. And is problems. First problems: the relation 3t equal to square root 3x plus 6 describes the displacement of a particle in one direction, where x is in meters and t is seconds. Find the displacement when the velocity is 0. Solution: the correct option is A0. 3t equal to square root 3x plus 6 is 3x equal to 3t minus 6 square. X equal to 3t square minus 12t plus 12. And the main formula: v equal to dx divided by dt equal to 6t minus 12 for v equal to 0 and t equal to 2 seconds. And the solution: x equal to 3 times 2 square minus 12 times 2 plus 12 equal to 0. Questions: ways to set the motion of a material point. Ways to set the motion of a material point. There are three ways to specify the point motion: vector, coordinate, and natural. Vector way: suppose a particle follows a phase in the plane as shown in figure first. In the vector method of specifying motion, the position of a point is determined by a radius vector drawn from a fixed point in the selected reference frame at time t. The particle is at point M, and at time t plus delta t it is at point M1. The vector r is the position vector of the particle at time t. It represents the displacement of the particle from the origin of the coordinate system. R equal to r of t is a vector equation of motion of a point. And now let us consider shorter and shorter time intervals. That is, we let delta t approach 0 so that the distance between points m of t and mt plus delta t also approaches 0. Figure 2, we define the instantaneous velocity vector as limit of the average velocity as delta t approach 0 v equal to limit delta t approach to 0 delta r divided by delta t equal to t r divided by dt. And the next questions. Collision theory, collision processes, and general collisions, elastic collisions. Collisions of particles. Collisions occurs when one object strikes another. Problems involving collisions are usually solved using conservation of momentum and conservation of energy. And there are two types of collisions: inelastic collisions and elastic collisions. Inelastic collisions, momentum is conserved, and inelastic collisions, momentum is conserved and the kinetic energy is conserved. The easiest collisions to analyze are completely inelastic collisions, where objects strike together after colliding. There is because energy is converted into what other forms in the collision, so we don't have to worry about conserving kinetic energy. Also, as we know that the two objects strike together, we have fewer variables to worry about when conserving momentum, and these collisions can therefore be completely solved just by considering conservation of momentum. And elastic collisions, in elastic collisions all of the energy remains as kinetic energy. No energy is lost to other forms. This means that for both kinetic energy and the momentum must be conserved. And an elastic collision between two particles. Before the collisions, the particles have a total momentum of pmava minus mvv, and the total kinetic energy of K equal to 1 over 2 ma times va square plus 1 over 2 mv v square. And collisions. When we talk about the collisions in physics, we mean that two particles are moving freely through space until they get close to one another. Then for a short period of time they exert strong forces on each other until they move apart and again moving freely. And the problems. 3 blanks of mass m1, m2, and m3 connected by cords are pulled by a constant force F on a frictionless horizontal table. Find a common acceleration A and B tangents T1 and T2. Solution: A acceleration equal to force divided by total mass, A equal to F divided by m1 plus m2 plus m3, and B tangents T1 equal to force acting on m1. The main formula: T2 equal to m1A equal to mv divided by m1 plus m2 plus m3. Applying Newton's second law of m2a equal to t2 minus t1, or t2 equal to m2a plus t1 equal to m1 plus m2 times a. And the solution, the t2 is m1 plus m2 times f divided by m1 plus m2 plus m3. Next questions: kinematic equations of motion of a material point. And kinematic characteristic of a relative motion of a material point. Let us observe that an arbitrary rigid body motion falls into one of the three categories: translation, rectilinear, and curvilinear motion, in which every line in the body remains parallel to its original position. The motion of the body is completely specified by the motion of any point in the body. And rotation about the fixed axis. All particles move in circular paths about the axis of rotation. The motion of the body is completely determined by the angular velocity of the rotation. And the general plane motion, any plane motion that is neither a pure rotation nor a translation below the general plane motion, can always be reduced to the sum of the translation and the rotation. Characteristic of rigid body motion: all lines on a rigid body have the same angular velocity omega and the same angular acceleration alpha. Rigid motion can be decomposed into the translation of an arbitrary point followed by rotation about the point. For arbitrary rigid body motion, VA equal to VB plus omega times RA divided by B, and alpha A equal to alpha B plus alpha times RA divided by B plus omega times RA divided by B, and where VB alpha B are the velocity and the acceleration of the reference, and omega alpha are the angular velocity and the acceleration of the body. And the next problems. A block of mass m1 sits on a block of mass m2, which rests on a smooth table. If the coefficient of friction between the blocks is mu, find the maximum force that can be applied to m2 so that my may not slide. And solutions: the main formula F maximum equal to m1 plus m2 times A. The condition that m1 may not slide is A equal to mu g, and F maximum equal to m1 times m1 plus m2 times mg. Next questions: variational principles and Hamilton's principle. Hamilton's principle is the most advanced variational principle of mechanics. The principle considers the motion of a whole system between two instants of time t1 and t2, and is therefore an integral principle. One remarkable advantage of this formulation is that it is invariant to the coordinate system used. And the next problems: two fluids m1 and m2 are in contact on a frictionless table. A horizontal force F is applied to the block m1. A finds the force of contact between the blocks. Solution: the force of contact Fc between the blocks is equal to the force exerted on m2. Fc equal to m2t, and with the acceleration of the whole system is the main formula A equal to F divided by m1 plus m2, and Fc equal to m2F divided by m1 plus m2. Fundamentals of Hamilton mechanics. Hamilton mechanics now considers the Hamiltonian formulation of dynamics. Define a Hamiltonian as a function of the two variables momentum p and position x. Hpx equal to px minus lx or x prime. Hamilton's equations follow immediately. L is not a function of p, and therefore dh divided by dx minus dl divided by dx. And next questions: basic theorems of particle dynamics. basic postulates of Newton's dynamics. The three Newton's laws are the basic postulates of Newton's dynamics, the fundamental postulates, and their consequences. We begin with some basic definitions. Definition first: a frame of reference is a system of coordinates used by an observer to measure physical quantities such as the position, the velocity, the acceleration, and etc. of any particle in space. And definition second: an isolated system of particles is a system of particles subject only to their mutual interactions, subject to no external interactions. Our first fundamental postulate of mechanics is stated as follows. Postulate first: a class of frames of reference exists such that for any isolated system of particles, a vector equation of the following form is valued: my and vy constant in the time, and we call mi the mass and pi equal to mi times vi, the momentum of the particle. Also we call p equal to mi, vi equal to pi, the total momentum of the system relative to the considered reference frame. And postulate 2: if a particle of mass m is subjected to interactions with particles m1 and m2, then at each instant t and the rate of change of these particles' momentum relative to an internal reference frame is equal to dp divided by dt equal to sigma dp divided by dt. The particle definition: a particle is a concentrated mass at some position in space. The inertial mass of a particle is defined through Newton's second law. And forces definition: a force is something that causes a particle to accelerate. Forces are defined through Newton's second law. Force has two properties: magnitude and directions. And next questions. Hamiltonian example. Hamiltonian example is for the harmonic oscillator example. The Hamiltonian is h of p of prx equal to px minus 1 over 2 mx squared plus 1 over 2 kx squared equal to p squared divided by 2m plus 1 over 2 kx squared, where we have had to replace x by p divided by m because h of px is supposed to be a function of p and x only. In summary, a discussion of Lagrangian and Hamiltonian dynamics has been presented, which should be suitable for advanced high school students who are interested in exploring some topics not normally presented in the high school physics curriculum. It is also hoped that this article can be given to students to read on their own. And problems. A block of metal of mass 2 kg by a light string passing over a frictionless pulley at the edge of the table. The block is subjected to a horizontal force by allowing the 0.25 kg mass to fall. The coefficient of sliding fraction between the block and the table is 0.2. Calculate A, the initial acceleration, and the B, tangent is the string. And the solution here, m1 equal to 0.45 kg and m2 2 kg and m equal to 0.2. And A. Initial acceleration. A as a main formula. A is m1 minus mu m2 divided by m1 plus m2 times g is A is 0.2 meter second minus square, and B we have the main formula t minus f equal to m to a, and t is t minus 3.92 is 2 times 0.2, and f equal to mg mu mg is 3.92 newtons, and is 4.32 newtons. Next questions, Lagrange equations. Lagrangian mechanics. With the agreement that the action integral is an important object, we give a name also to its integrand and call it the Lagrangian. In the examples that we considered so far, and in fact in most cases of interest, the Lagrangian is a function of a set of n variables qt and their n first order derivatives q1 as q of t equal to t2 or t1 ddl times qt q1. We use q to denote the coordinates because the Lagrangian formalism is very general and can be applied to all sorts of systems where the interpretation of the variables may differ from the interpretation of x as a position of some particles. The space on which q1 as the coordinates is called the configuration space, and the pair q and q prime determines the tangent vector at the point whose coordinate is q. Taken together, q and q prime are coordinates on the tangent bundle of configuration space. The dimension of the tangent bundle equals that of phase. The scope of Lagrangian mechanics. Among all those functions qt of t for which qt of t1 and qt of t2 are equal to some arbitrarily prescribed values, the action functional has an extremum for precisely those functions qt of t which obey the Euler-Lagrange equations. Is equations dl divided by dq1 minus d divided by dt times dl divided by d1 prime is 0, provided such functions exist. An important difference between gravity and electricity, also in the non-relativistic case, is that particles coupled to gravity throw the mass, and all particles have a mass, while only some have electric charge. Moreover, the mass of serving as charge for gravitational force is the same as the mass occurring on the left-hand side of Newton's equations. And the second question, collisions of particles. Collisions of particles. Collisions occur when one object strikes another. Problems involving collisions are usually solved using conservation of momentum and conservation of energy. And there are two types of collisions: inelastic collisions and elastic collisions. In elastic collisions, momentum is conserved, and elastic collisions, momentum is conserved and kinetic energy is conserved. And next problems. As a constant forces f1i plus 2g plus 3kn and f2 is 4i minus 5g minus 2k and act together, and particle during a displacement from position r2 is 7k centimeter to position r1 equal to 20i plus 15g centimeter. Determines the total work done on the particle. Solution. First one, net force F equal to F1 plus F2 is 5i minus 3g plus k, and is displacement r12 equal to r1 minus r2 is minus 20 minus 53 minus 7 centimeter, and the work done. W is F times R12 is minus 0.48 G. And next problems, a small ball of mass m is projected horizontally with velocity v. It hits a spring constant k at inside an opening of a block resting on a frictionless horizontal surface. Find the compression of the spring, knowing that the block will slide due to the impact. And we work out in the CM system the total kinetic energy available is SMS is K is 1 over 2 mu v square, where mu is m divided by m times m divided by m plus m is the reduced mass. If the compression of the spring is x, then the spring energy will be 1 over 2 chi square, equating the total kinetic energy available in the SM system to the spring energy. The mean formula 1 over 2 mu v squared equal to 1 over 2 kx squared, and the x is a v square root m divided by k is a v square root m times m divided by k times m plus m. And next problems. A helicopter of mass 500 kilograms hovers when its rotating blades move through an area of 45 m2. Find the average speed imparted to air. Density of air 1.3 kilogram divided by m square, and T is 9.8 meter divided by second square. And the volume of air moving down per second is A, where V is the air velocity moving down through an area A. And the mass of air moving down per second is rho a v square, and the erection force upward is the helicopter's weight. Is the main formula rho a v square equal to m times g. The main formula v is the square root m times g divided by rho a, and is 9.50 meter divided by second. That's all.